Welcome to the Henstitute. Today we're going to look at a situation which is going to include elastic potential energy. We haven't had that. So if you notice, I have a spring over here. Spring. And this spring is going to have elastic potential energy when this mass up here, this huge mass that's going to fall, falls down on it. And so just to make it a little bit easier, I'm going to assume it's a 5 kilogram mass. It's going to start off with no initial velocity. It's going to fall from 13 meters above this spring, and the spring has a spring constant of 240 newtons per meter. What we're going to try to figure out is when this block hits this spring, it's going to compress it. So it's going to cause it to push down and come to some final compression. This is what we're going to try to find. I want to know how much is this thing going to be compressed. So initially, it's not going to have any compression. So this is equilibrium for us, which means that its initial compression is 0. So that's going to make it a little bit easier as we kind of go after this. So the idea is this block is going to fall, land on this and compress it down. So it's going to squish it down, and we're going to try to find how much it squishes it. And at that final position, the other thing that's going to happen is it's going to also have a final velocity of 0. In other words, we're going to have it compress until it comes to a stop. Now, as I get ready to do the MegaWork energy equation, one of the things I always go through is I try to see if I can eliminate anything. So when most people look at this, they're like, hey, there's going to be work being done because there's work done by gravity. Gravity's going to pull it. It's applying a force. And the spring is going to apply a force. And that's true. However, gravity is going to pop up in our gravitational potential energy, and the elastic potential energy is going to explain the spring. So what I'm looking for are other forces. If this had some kind of air resistance on it, or if someone pushed it as it was coming down, or something to that effect. So in this particular case, we're going to assume that there is no work being done by external forces. And since there's no work being done by external forces, we don't have to include that work. The other one that always throws people off is kinetic energy, because they're like, oh yeah, you drop it, it's going to be moving. Yeah, it's going to be moving. It's got kinetic energy. It's got energy of motion. However, if you notice, it's going to start off with an initial velocity of 0. We're going to have it fall until it hits this spring and then compress the spring down. And we want it to have a final velocity of 0. So we want it to stop. Therefore, it doesn't have a change in kinetic energy. Does it have kinetic energy while it's falling? Of course it does, but it does not actually have any initial or final kinetic energy. So the change in kinetic energy is also going to be a 0. So I'm going to use the magic of the eraser, and I'm going to erase those parts. Now, when I do that, one of the things I have to take into account is I still need to keep this equal sign, but now what I've done is I've put 0 over on this side. So there is no work being done. So really what I'm going to have is 0 is going to equal a change in gravitational potential energy plus a change in elastic potential energy. Really what ends up happening if I kind of move things around is the gravitational potential energy is going to equal the elastic potential energy but become the opposite of it. In other words, it's starting out with gravitational potential energy that's going to get converted into elastic potential energy. This is sometimes called energy conservation that we're dealing with. So let's start putting our equations in. So I'm going to still leave a 0 over here on the left side. So 0 equals, and then we'll go into our gravitational potential energy. That's normally mass times gravity, and it's going to be final height minus initial height. And then I'm going to come over here to my elastic potential energy, and that's going to be 1/2 the spring constant, since that's going to stay the same. And it's the final compression or stretch squared minus the initial compression or stretch squared. Now, one of these I can actually get rid of because I noticed that this spring is initially in equilibrium. In other words, it's not being compressed, it's not being stretched, so it's just sitting there, nothing's on it. So it has no initial elastic potential energy, so we can get rid of that. Now, the other thing that commonly happens with this problem is people always want to say, hey, isn't the final height going to be 0? Can't you measure height from wherever you want? And people usually go, hey, aren't you going to measure your height from here? So won't this be the 0 line? And that's where it's going to go. But you have to take this into account. So the block, and they pointed it like this. They just have these little points on here. If you notice, there's little points on the side here. That's just so that the block, if you were to truly do this, wouldn't fall off the spring. So we're measuring everything from the bottom of this thing, if you notice. And so our initial height here is actually this 13 meters. So it's starting 13 meters above the spring. But it's not going to stop there. It's going to compress the spring and cause it to go down. So the final compression that we're actually trying to find is actually also going to be the final height. But the weird part is that's going to be below 0. What happens to a number when it's below 0? It becomes negative. So my final height is actually going to be the opposite of that compression. So it's going to be minus XF. That's going to be a little bit weird as we go about trying to solve this. So I'm going to start putting some numbers in. So I've got 0 equals, I've got my 5 times 9.8. For the final height, I'm going to put negative XF. That's kind of weird, but we still have to do it. I'm going to subtract my initial height, which is 13. And then over here, I'm going to add to it 1/2. 240 is my spring constant, and then I just have XF squared. So XF is going to be the square of that. That's going to be my final compression. I don't have to worry about putting a negative in there to talk about it being compression because everything is squared when you're dealing with elastic potential energy. So you have the same energy stored whether you compress it or you stretch it a certain distance. Now, if I notice, I can simplify a few things here. Let's go ahead and I'm just going to switch over and do all this in black. So I've got 0. 5 times 9.8 is actually going to be 49. And then I have it times negative XF minus 13. And then plus half of 240 is 120. And that's times XF squared. Here's the bad part. I've got an XF squared that I'm trying to solve and an XF in here. So unfortunately, this is going to be quadratic. So I'm going to rearrange this so it looks like a regular quadratic formula and a regular, basically an AX squared plus BX plus C format so we can easily solve this. So I'm going to put my 120 times XF squared first. And then I have this minus 49 times XF. And then I've got 49 times a negative 13. So I'm going to need to calculate what 49 times 13 is. Let's take my calculator, times 13. And I've got 637, but it's subtracted, so it's minus 637. And all of that equals 0. So now what I've got is I've got it in this format where this is my A, x squared, this is my B, and this is my C, and I'm going to go about actually trying to find out what XF is using the quadratic formula. Since I have this saved on my calculator, I'm going to go ahead and just use my calculator to solve this. Okay, when I use my calculator, I actually come up with 2 possible answers. My calculator gives me 2.517177121, and it gives me a negative 2.108843788. And you look at both of those and you're like, I don't know which one to pick. Hopefully your first instinct is not to pick the negative one, to say we shouldn't be negative because this is an X value and it's a measurement. And you're actually correct. Now your other instinct though is you look over here and you're like, it's going down. Shouldn't that be a compression? Shouldn't that be negative? But it's actually not. So notice over here, I picked that my height was an opposite of XF because it was below 0. So I've already taken into account this little negative right there. But when I'm putting in XF, I'm just putting it in as a solid positive number. So that's what I'm going to keep it with. So I do not want the negative root. I only want the positive root up here. And so I round that. It looks like I've got 2 sig figs. So let's round it to just 2 sig figs. And I would say this is 2.5 meters because it's a displacement, it's a stretch or compression. And there we have solved a megawork energy problem with a spring involved. Hope you enjoyed this edition of the Henstitute.